Hi, I'm Hugh Hoagland, and we're here to do low voltage electrical safety based on NFPA 70E today. There's several things we're going to do today. The order of our day will be electrical safety facts, regulations and standards. We'll look at electrical hazards and protection strategies, personal protective equipment, hazard risk assessment, and safety-related work practices. We're helping you meet the requirements of NFPA 70E and the OSHA requirements for electrical safety. Your job may include being an electrician, it might be a maintenance tech or something like that. We're wanting to help you understand the electrical safety rules in NFPA 70E that'll help you comply with all the OSHA regulations for electrical safety and help you not to get hurt in the workplace around electricity. You should have in front of you a couple of books. You should have the E-Hazard Workbook, which is our workbook. You should have the NFPA 70E standard, and this class is on the 2015 standard. Those two in front of you will be needed for some of the exercises that will come up a bit later. You're going to fill out an evaluation of our class. You're going to fill out a form of the different work practices and exercises that will come up, and then you'll also have some other pieces of information that you'll fill out and fax back to us, or it'll be graded by your instructor there on your site. Now let's talk about electrical safety facts. What are three habits that you have when you work around electricity? Now, if we're in a classroom setting, we actually just write these on the board. And people often say things like lockout, tag out. They say things like wear my PPE. And those are all good things. And we're going to talk about many habits that you can get into when you're working around electricity that will prevent injuries. One of the most important habits is always actually making sure that there is no power on the circuits you're working on and that those circuits cannot become re-energized. So a good lockout tagout procedure is important, but if you know of something that your procedure may not quite cover well, it's really important to make sure that the power can't come back on, either by backfeed or by another source or someone turning the power back on. Lockout tagout can be a big part of that, but also verifying that the energy is gone. We'll talk about all these things as we go along, but these should become habits. They're things you do every single time you work on electricity to keep you safe. So why should I be concerned about electricity? Well, first of all, it's for your own safety and also for the safety of your fellow workers. And on our slide we say to comply with applicable regulations. We want you to go home safe every night when you get finished with work. I'm going to tell you a little story about somebody who actually had a real problem at work, and it was an electrical incident that happened, and kind of talk about how that could be prevented, but it's us being concerned about that because this could happen to anyone. Tim actually worked on an office building. He was a commercial electrician. He did commercial and residential, light commercial, and he was working in an office building on a 480 cabinet. Tim knew that 480 was dangerous. He was very careful. He was a good quality electrician. He actually taught the National Electric Code at his local community college. Tim was involved in this particular night. He was working on an EMON-DEMON meter. He was working with Bill, his partner, and Bill was a longtime electrician with Tim. Tim was a great troubleshooter. Having taught the National Electric Code, he knew the ins and outs of pretty much everything. And in this particular night, it happened about 2 o'clock in the afternoon. He was going to get off at about 5. He had to be at a soccer game at about 6. He said that he was worried about making sure he made it to the soccer game for his kids. He had about 5 kids that were at home. Only one of them was he and his wife's. The other ones were another father, and that father, according to him, was a deadbeat dad, didn't pay child support, wasn't really involved in these kids. And there were 4 boys that this guy had with this lady, and he wanted to make sure he was there for those boys. So a good person who cared, probably like you, who wanted to do the right thing. And that night, he was a little flustered, making sure that he got this job done and may have pushed the speed just a little bit. So Tim goes in, he opens up the 480 cabinet. He's going to repair or replace a EMON-DEMON meter. He knows several things usually happen. Usually it's the CT is bad, or there's a connection on the CT or the connection to the actual meter. And typically that's what's wrong. Once in a while, a wire could be bad, but most of the time it's the CT that's bad. So he needs to find this CT. When he opens up the cabinet, he describes it as a rat's nest of wires. He can't find this thing anywhere. So he sends Bill out to get wire, another CT, and another EMON-DEMON meter, just in case. They have them on the truck. He wants to make sure he can do this job as efficiently as possible, not only for the time, but also so he can make that soccer game. So as he's doing the job, he's opened up the cabinet. He looks, he can't find this CT anywhere. He's looking inside the cabinet. As he looks in that cabinet, he sees a area about this big. It's a nylon cover, a black nylon cover. It's got nylon screws on it. It's a dielectric cover. Has a warning label on it, the lawyers pointed out in the lawsuit, that said, do not remove when energized. He was looking to see if the CT was back behind that cover because it wasn't anywhere that he could see. It actually was behind some other pieces of equipment, but he couldn't see it at the time. As he removed that cover, it blew up. It arc flashed. It ignited his clothes. They started to burn. It burned his whole shirt off before he actually got outside. He ran outside of the building trying to get the fire out and trying to get the t-shirt off his body. He was pulling at the t-shirt, and Bill noticed that the t-shirt wasn't on fire, but his blue jeans were on fire, and they were burning down toward his knee. Bill took him, threw him onto the ground on the asphalt, and put out the blue jean fire with his bare hands. Now we don't have one person hurt, we have two people hurt. Bill's burns were second and third degree burns. He did regain the use of his hands, but he had scarring on his hands. Tim had about 45% upper torso body burn, and Tim's going to be hurt really for the rest of his life. He was basically almost disabled. He did come back to work in about 9 months because he was only getting about 50–60% of his pay on workers' compensation, which is not the best way to end your career, and he had those 5 kids to support. He worked there until the lawsuit finished itself, and he was able to recoup some of the money for the medical and all the different things that were involved with that. But when you look at Tim's situation, not cutting those corners, and we're going to talk about the corners that were cut, we're going to talk about equipment design issues and things like that, and knowing what PPE to wear and wearing it every single time will make the most difference in your life. Now, there are a lot of statistics out there about electric arcs and statistics about electrical safety. And the statistics say that there's 4,000 non-disabling electrical contact injuries every year in the workplace. There are 3,600 disabling electrical contact injuries every year in the workplace. Those numbers may have gone up, they may have gone down since they were tabulated by NFPA, but they're rough numbers that give you an idea that this does affect a lot of different workers. Now, every other day, somebody dies in the workplace, and it's almost every other day. When we first started doing this training about 20 years ago, it was actually 2 people every day were dying in the workplace from electrical accidents. And now that has dropped quite dramatically because of training like this and because of following good rules and because of wearing the right PPE and doing the right things. But it's still the 5th leading cause of fatalities in the workplace, traumatic occupational fatalities. The only thing that beats it in the workplace is fatalities where someone kills somebody in the workplace, and that doesn't happen to electricians very often. It happens mostly to convenience store workers and also to cab drivers. But the most common thing that you would come against in the workplace would either be a fall or electrocution or arc flash. About 2,000 people, according to the statistics, the older statistics, are actually sent to burn units every year with electrical burns. And we don't want you to be one of those people. That's why we're going to give you this training. There's a study about electric utilities, and in that study they looked at both their low voltage and their high voltage people, and electric utilities have a lot more electrical work than the average industry. But in those electric utilities, there were 120,000 workers, and over a 10-year study, there were an average of only 125 injuries per year. This is electrical injuries. There were other injuries that were not counted in this study. 77% of those included arc flash injuries in the actual injury, and 21% were permanent disabilities, and 2.4% were fatalities. When you look at the numbers, there are only 125 injuries. That's not really that many people being hurt, but 77% having arc flash was something that was actually really new at the time when this study came out. The other thing that was really important about this study was that 25% of the people that got injured never went back to work again. 2.4% fatalities, 21% permanent disabilities. We started tracking the U.S. statistics back in 1994. And it was several years in a row from 92 to about 94 that we had between 600 and 650 every single year that died of electrical accidents. What we've seen in the last 10 to 20 years is those accidents that became fatalities have really begun to drop. And they began to drop in 1994 when OSHA put in a law that said that clothing cannot increase the extent of the injury in the case of an electrical contact or an arc flash. It means that it can't ignite. Now, that was only applying at that time to electric utilities, and that standard didn't change until really just this last year in 2014 when it was upgraded quite substantially. But when you look at this particular type of accident that leads to a fatality, these electrical accidents are somewhat unforgiving. But remember, only 2.4% of all accidents that are electrical are actually fatalities if that study was right. And that study was actually for a whole country. So it's quite interesting. Now, when you look at the fatality dropping, why do they drop? There are really two big reasons. Number one, more electricians today actually wear electrical shock protective gloves and electrical shock protective sleeves when needed. So rubber insulating sleeves have saved many, many lives, and they've really become much more pervasive throughout electrical industry every time you work on electricity, whether you're doing voltage testing or you're actually doing a live electrical work. You wear rubber insulating gloves and or rubber insulating sleeves. That's saved many, many lives. The second thing that's really saved lives is having ARC-rated clothing that's close to being matched to the hazard. When you match it to the hazard, most people walk away with no injuries or much less injury than they would have gotten before. And so we're seeing fewer and fewer people dying when we're looking at arc flash because we're wearing the right PPE. And that's one of the biggest changes that have come about. Now, we've talked about this 2.4% fatalities, or almost 25% of the people who get hurt and don't go back to work. Well, that doesn't really work out in normal safety. In normal safety, it's more like the pyramid. In the pyramid, we have one fatality that's usually preceded by 30 lost time injuries, 300 recordable injuries, 30,000 near misses, and 300,000 at-risk behaviors. Now, this is not the best model, but it's a model that kind of gets across to everybody. It's a little more of a 3D model. It doesn't work the same. Those numbers are not the same for every single behavior. So in electrical safety, we kind of do a little shorter pyramid, and we say it only takes 10 recordables to wind up being a fatality because it's much less forgiving. It's almost a 10-to-1 relationship between having an accident that somebody finds out about to dying or being really badly hurt from that accident. U.S. industrial low voltage fatalities actually are quite interesting. They let us know that most of the people who die in the workplace die in 110 to 120. This was a 1998 study by NIOSH back when electrical injuries were at a pretty good peak. And they wanted to look at what was causing this and what was the voltage. And the voltage actually most commonly was 110 to 120, and then 220 killed quite a few people in this particular study. This was only of the metals industry, and 12 people died from 277, 480 to ground, and also 480 volts killed about 16 people. So when you look at this particular study, it lets us know that 110 to 120, we think that's not that dangerous, and I know what I'm doing around that, but that's the one that's most likely to kill somebody in the workplace. Now, the other interesting fact when we look at these statistics, we find out some other interesting things. First of all is that the people you think would die are not the ones that usually die. The beginners, as I call them here, the 16 to 24-year-olds are less likely to die working on electricity in the workplace. The most likely age group to die is not the survivors, the older folks, and that's actually my age group now. We're not likely to die. The most likely person to die, I like to call them the cowboys. We actually changed this for a few years in our training. We changed it to daredevils because we didn't want to be gender specific, but what we found out was there's a lot of studies that have been done as who's the most likely person to die in the workplace. In the study, they found the most likely person to die in the workplace of any cause is actually an adult male who's highly intelligent, who's very outgoing, that cares about how other people perceive them, and who basically cuts a corner and then winds up dying. And they're in that age group between about 25 and 35. That is most likely to be the outgoing worker. It's the worker that has lots of experience. It's the worker that has lots of knowledge and has kind of figured out ways to cut the corner sometimes. And that's the person who's least likely to think that they're going to be the person that would die in the workplace. So following the rules every single time does really make a difference. These accidents can happen to anyone, anywhere. And we developed this accident looking at newspaper accounts, and we're involved in some of the accident investigations. It was interesting because it showed some of these same principles that we've talked about. First of all, it happened in a place nobody expects, just a Walmart. It was fed by a 12,000 volt system. There were 3 workers involved. One of the workers died after the accident, and that worker died 51 days later. Now, I don't want to go into the pain that that worker was in, but what it points out is that 51 days later, there were also 2 other workers that were still listed in critical and serious condition. 3 workers got hurt in one incident because of one cut corner. And it was not testing the circuit. They were actually low voltage electricians. It was a high voltage to medium voltage line that was still energized that they assumed had been turned off. And they were hurt because of that. And the last thing that's interesting about this, these were young workers, but they were not inexperienced. The workers were between 29 and 35. They all 3 were journeyman electricians. They were union workers. They were involved in a very high-profile job, and they were doing exactly what they should be doing, but they cut a corner here and there. They got comfortable cutting those corners. Regulations and standards. We'll talk about the OSHA standards, both the Subpart S and the Subpart K. We'll look a little bit into Subpart V. We'll also look at 70E standard, which has a similarity to Z462 standard in Canada. If your company does work, the rules are exactly the same in the US as they are in Canada. And also the National Electric Code, which is similar to the Canadian Electrical Code, and the National Electric Safety Code, which is also similar to a CAN-UL standard S801. People use these electrical safety principles that were developed in the U.S. standards groups all around the world. We'll look at ASTM standards, IEEE standards, a lot of different standards that will apply to your work. Now we're going to talk about the OSHA standards. The OSHA standards are enforceable as law. They're performance-based language, which means that they tell the employer what has to happen. They don't tell them always how to do it. For example, in electrical, they tell us that we have to get our rubber gloves tested every 6 months, but the OSHA standard never tells you when to wear a rubber glove. But what OSHA actually tries to do is they try to enforce things that they think people won't do naturally. Actually, OSHA was updated in 2014, but that main standard for electrical safety, especially for utilities, wasn't updated since 1994. That's why we encourage you to use the NFPA 70E standard for your electrical safety program. OSHA requirements are two types. The general duty clause says the employer has to keep the workplace free from recognized hazards. That's a really broad clause. It's actually used in 40% of OSHA citations. What the general duty clause is trying to accomplish is it's trying to say that you have to look at your workplace, determine what's dangerous, and make sure workers don't get hurt on that. And that's something you help your employer with. You look at the workplace, you determine what's dangerous, and you don't get hurt on that. That means you're meeting that general duty clause. When someone gets hurt, even if there wasn't a standard, even if OSHA didn't have a rule against that, if you knew that it could hurt you or your employer knew that it could hurt you, they're responsible for that particular action. So it's important to understand the general duty clause. Then there are specific duty clauses that we'll talk about that relate to electrical safety. Many of these are covered in 70E, many of them are covered in the OSHA standard. We'll give you citations for both on the slides, but I'll just talk about it, how they actually apply, because that's what we care about. If you understand the concepts, you don't have to know where it is in the standard, you don't have to know what standard it's in. Understanding the concepts, doing it right every time, means you don't get hurt, and that's really what matters. Specific duty clauses. Electrical protective equipment is in the standard. So if you want to turn and look up these particular citations, stop the video here, look up these citations and get a broad understanding, and then come back to the video and I'm going to explain these to you. But I want you to read all these citations. They're in the back of the eHazard workbook. We'll give you the page numbers on the screen. Freeze the video at that page, look these citations up, talk about them among yourselves for just a few minutes, then come back to the video and I'll explain some of the principles. So now you've looked those things up. Some of them you may not know actually existed, and some of them you probably don't fully understand. 1910-335-A1I, the section about electrical protective equipment, we asked the question on the screen, was that related to arc flash clothing? Actually, it wasn't when it was originally written. It was originally written talking about rubber goods cover-up, things like that, rubber insulating gloves and sleeves. But over time, it's changed its meaning because electrical protective equipment wasn't actually defined in the standard, and it actually could mean arc flash clothing now and has been cited as such. So it's a good idea to realize that whatever equipment you use to protect you from electricity, that you use that equipment, and it's required that your employer provide whatever's required for you to use in the workplace. The eye protection was required to be a face shield and or eye protection for the eyes, safety glasses or something like that, since 1991 to protect from arc flash. Yet in 1991, there were no arc flash rated shields. That didn't happen until about 2002. So these standards changed. The OSHA standard may be the same. It's an underlying performance-based standard, but how you comply with that standard may change over time. 70E got very prescriptive. It says when you're exposed to this, you wear a shield. When you're exposed to this, you wear a hard hat and a shield. When you're exposed to this, you wear a hood. So there are lots of different things that change over time. The OSHA standard, because it's very general, may remain the same. So how you comply with this particular section is something to think about. Same thing with insulated tools. They didn't actually have a standard for it until after 2000. So the insulated tools were required in 1991 when you worked near live parts, if you read that standard. Well, near was not defined by OSHA. So what's the distance of near? 70E prescribes that as the limited approach boundary or the restricted approach boundary. So get into the standards, read what they're talking about, and understand where those distances are and how your tools and your rubber goods and all those things are to be used and when they're to be used.